All right, we're going to explore a new reaction called the Henry reaction. Wow. In fact, that's not fair. We should call it the Henry reaction. Yes. Henry. It's French. And the last mechanism is my favorite, this test. Let's go pink. This mechanism here is called TIFFENEAU-DEMJANOV. And it's got a rearrangement in it. In the shadows, they're lurking. Tiffano-Demyanov rearrangement. It's one of the rare times I actually like the name, only for how they sound. It just sounds poetic. Tiffano-Demyanov. It's beautiful. Okay. So what do we have going on with the Henry? Well, we have a nitroalkane. I don't believe we've ever seen one of those. We've seen nitro before. I don't think you've seen it on an alkane. And believe it or not, this is an H that's alpha to the most electron withdrawing group, and it loves resonating. It's got both going on. So to make an anion there is rather easy. So easy, I would expect you to guess the pKa. So what would be a pKa that you're supposed to be able to guess every time? It's the most common pKa number we've ever seen. There's about 5 molecules that have this pKa. Okay, it's not that common. We've only had 120. We've had about 5 10s. Yeah. pKa equals 10. No, that list of strong acids will never change. So we're stuck with a -5. But back in the day, if I said guess the pKa, there's all chapter I was saying every time I make you guess, just guess 10. And I guess I didn't say it this semester. So. But you'll see videos where I actually do that. Guess the pKa. It's always 10 when I set it up like that. So yeah, it's easy to get that H. We like 10. 10 is nice. We can take it off with a cheap, strong base like hydroxide. And we're making an alpha anion. Want me to prove it? Here it comes. Got your propyl. That's the alpha position to a nitrogen instead of a carbon. Don't forget it's a minus. One thing I didn't tell you, the Henry is an aldol using a nitroalkane anion. That's what we have right here, anion. And we know the aldol inside and out. Red first, blue second. Attack carbonyl, make sigma. Very exciting stuff. Second step, O- becomes OH. It picks up a proton from the solvent. Done. There's the done. Yeah. I just want to remind you, one of our activities the other day, I said this is so important. There's 4 ways, but there was really 5. Can you give me one of them that reduces NO2 to NH2? Anything. Anything. H2PT is a good one. Give it a shot. I do have one small objection to that particular choice, though. You just reduced your alkene to an alkane, so it wasn't a good choice. In fact, that would be the first reduction that happens. The C double bond to C becomes CH2, CH2. So this is probably one where you would want to use maybe lithium aluminum hydride, HCl, not 4 others. H2PT is off the table. Alkene goes to alkane. Good to know. What are the other ones? Tin, HCl is okay. That won't touch an alkene. Iron HCl is okay. H2 and nickel's not really okay. Same reason. Those are red X's. Don't do them. So 2 other ways. 2 other ways. And they're checked off below. Yeah, the ones that reduce alkenes, not a good choice. Now we're going to do the famous diazotization mechanism, which you will have to do on your exam no less than twice. And I think it comes in at 6 points each time for a not hard mechanism. So don't blow it off once because you'll be really blowing it off twice. NaNO2, usually on a test, and I won't have it drawn like this on the test. I will have it like this for you. O, N, double O. I may have the Na on there, but it's just a little nicer drawing. So what do you do first? Cross off the spectator, lone pair on the O, it's on the anion, grabs the H. Cl minus leaves. In the next part, well, let's do the next part next. You now have H bonded to O, bonded to N, double bonded to O. And your goal is to get here. N triple bond O. And if you're worried about what happened to water, here it is. There it is. And there's a plus charge on an O with 3 bonds. So get me there. In a reaction you've never seen before. Should be able to get me there at this time now in your career. How do you get that HO to leave in a reaction where HCl is present in large excess? Protonate it. Yeah, thank you. You made me happy. H bonded to Cl. Lone pair on O. Step 1, protonate. Step 2, eliminate. Lone pair on O. We already wrote over there, blue second. Don't have to write it again. And triple bond. Had a double bond, now it's triple. Didn't like the way that worked out. Wanted to look clearly like a double bond. There. And leaving group leaves. Baby blue. And that gets us to that N triple bond to O. N triple bond to O is the nitrosyl cation. And write it down here. Gets its own little box. They love nitrogen. Got a shadow box going here. Haven't tried this in a while. Yellow. Ooh. Yellow shadow box. Oh yeah. Nitrosyl cation. Cation. Whoa. Haven't had that one in a long time. We've been very fortunate. When was the last control save Dr. Whitaker did? We'll find out very soon. Wait, we might have got away with it. That usually was a symbol for a crash. We'll see. I think we're safe. Okay. So we got this, which loves amine. Here's your amine right here. Here's your amine. I think just to get the ball going here, I'm going to circle everything except for the nitrogen. Call it R. Lone pair on the nitrogen is strongly attracted to that other nitrogen. Strongly. Oh, wow. How am I going to even do this? Things are a little tight around here. Can I just take it from the top? We just labeled R, right? R is attached to NH2. Didn't change a thing. There's the lone pair. Didn't change a thing. Here's my nitrosyl cation. You ready? Just putting it over here. And this comment here, comment goes for there. There it is. R, bonded to N, 2 bonds to H, new bond to N, with a double bond to O. And we got to get into the boxes up here. We clearly have a lot of work to do. And I'm going to lose a half point if I just leave this drawn like this. Uh-oh. I'm going to lose a half point. Formal charge. Nitrogen, 4 bonds, had a head nod out there. Light head nod. Said, yep, that's plus charge. Hey, I'll do the mechanism here and you tell me what I just did. Just from the arrows. We got a Cl minus here. We got an HCl down here. Acid-base conjugate pair. Base. Grabs one of those H's. I'll grab that H. Sigma becomes pi. Old pi protonates. What is the name of this process? There's resonance involved. It's a tautomerization where you move the double bond and a pi bond. Sorry, double bond is a pi bond. You moved a hydrogen atom and a pi bond. My apologies, I misspoke. You moved a hydrogen atom and a pi bond. That is tautomerization. And do what looks like tautomerization again to finish this thing off. But you got to make the O leave. So what do we do first generally to make the O leave? Protonate it. Yeah. So once again, you're going to need the pair, Cl minus and its conjugate partner. First step is to protonate to make better leaving group. And then do what looks like tautomerization, but technically is an elimination. They're close cousins. Their arrows almost look identical. And that gets you into that box, doesn't it? N triple bond to N. That's an alkyl diazonium ion. Yeah, sounds fancy. Alkyl diazonium ion. A little white out. Right there. Where? Okay. And then we're going to do the rearrangement step. There's rearrangement here and rearrangement here. I think it's pretty easy if you put numbers down. Well, not incredibly easy. But if we go 1, 2, 3, 4, 5, 6, and A, we see that 1 has a double bond in both cases. A is the one with the ethyl on it. So 1A is a bond that exists already. So that's not a new bond. 1 is bonded to 2 here, bonded to 3, 4, 5, 6. And 1 is bonded to 6 here. 6, 5, 4, 3, and 2 is bonded to A. 2 is bonded to A is a new bond, and 6 bonded to A is a new bond in the first one. Should I put the new bonds in with a highlighter? That's a new bond. And A bonded to 2 is the new bond up there. Those bonds did not exist before. Tell us what to do, don't they? In both cases, I'm going to scribble out the H and put it back on as a bond. There we go. Scribble, scribble. Scribble, scribble. Cl minus is going to take the H. You could use water, I don't care. Cl minus is here. You're going to make a pi. The new bond is between A and 6. So the old bond was 1 to 6. It doesn't exist anymore. That tells you where your arrow has to start. 1 to 6 doesn't exist in the end. That's the pair of electrons you need. Where does it go? It goes from 1 to A. No, sorry, 1 is already bonded to A. 6 to A. Sorry, misspoke. 6 is now bonded to A and you're done. Same story here, except you're going the other direction. Cl minus grabs H. Oh, I should have been a little more stealthy. Going on the top. Cl minus comes through the alkyl diazonium wording. Makes sigma becomes pi. This breaks and goes there. There you go. 2 is now bonded to A. Same labels as above. And that's it, the Tiffany-Demyanov rearrangement there. There's one video where I really get into me liking the name, and I talk about these guys, and I talk about their chauffeur Henri. I like it. I had fun making that video. Yes. The first one, sorry? Oh, nitrogen didn't leave. Oh my goodness. Thank you. You can't have nitrogen leaving without an arrow showing it leaving. Ooh, that's a close one. Good eye. Yeah, there we go. So, other videos. It's a nice one. And end.